What is this? It's a rocket ship. No, that's my soldering base station. Here, we have a new circuit here. Simple circuit. We have the LED, transistor, some resistors here, and resistors there in the LED, and a push button here. With 12 volts power supply, my invention. Push the button, LED turns on. It is a transistor as a switch. Simple as that. Push the button, transistor conducts, and the LED turns on. Push again. Oh, as simple as that. Release the button, the LED didn't turn on. Let us see the circuit. Now we have the circuit here. A transistor C547C base resistor to limit the current flowing the transistor, damaging my transistor, and the switch here, and I put the output LED here in series with the supply. This is my design with a current limiting resistor here to limit the current flowing in the LED in order not to damage my LED. LED is 10mm red. Emitter here. See the circuit. Current flows here when you push the button. Current flows here, conducting the transistor in saturation, and then current flows here to the base, to the emitter, back to the ground. So we calculate the value of RD here. We don't know the value of RD here, or resistor of the value of the diode and the base resistor here. So I know the data sheet. I have the data sheet of this transistor and data sheet of this LED that is given. So voltage collector at saturation, it's 0.05 of the transistor. IC collector current is 0.25 ampere. Now that's the current flowing the LED given. BC sat here at the table, 900 millivolts. I divided it into 5 or 4 to get that 0.05 volts. If the IC is 100 milliampere, I'm using IC is equal to 25 milliampere just to turn on the LED to saturate the voltage. Here, this one, collector to emitter saturation. If IC is 100 milliampere, typical value of collector emitter saturation is 200 millivolts. Divide this by 5 becomes 20, divided by 4 becomes 25 milliampere, and this one becomes 0.05 Ohm's law. Since current here is in series, current of the diode is equal to the current in the resistor here. So we got, using my favorite magician, Ohm's law. Ohms. Voltage over current equals, oh, what's this? Oh my god. We have a resistor value of this transistor, 2 ohms. What is this? Let us check the other schematic diagram here. NPN transistor, the value of the diode, 10mm red, 2.1 volts, data sheet here. Calculating the RD here, series, Go using my magician, Kirchhoff's voltage loop here, current goes here and here, completing the circuit. You will get the voltage across RD, this one. Since we know the current in the diode, which is 25 milliampere, and the voltage here, we still don't know the voltage. This is Kirchhoff's voltage loop here. Supply plus PRD plus BD plus BSAT. Since if IC is 100 millimeter, according to data sheet, BSAT must be divided by 4 becomes 50, because IC divided by 4, 25 milliampere. We only need 25 milliampere current flowing here to saturate the transistor. So we've got BC set 0.5 here, KBL on that loop. We got the voltage supply minus the voltage diode BSAT 9.85, the RD voltage of the RD using Ohm's law, my magician favorite, 9.85 volts voltage RD. Resistor here is 400 ohms. Now we have here, according to the experts, IC is equal to HFP IB. What I want the IB here is 25 milliamperes, so I got 25 ampere converted already in ampere. Divided HF is 120. According to the table here, 120. Where is that? Typically 120 here. If the collector current is 100 milliampere, it's along 100 milliampere. Because we're operating in 25 milliampere, we need the 25 milliampere here to saturate this transistor or to flow the current here. So we have that IB is equal to 0.00121A, RB is equal to B over I. That's Ohm's law, Kirchhoff's voltage law at RB. Here supply, voltage drop here, goes here, goes here, and there we got this voltage drop here. Since you know BSAT 900 millivolt according to the table here, 900 millivolt voltage to emitter saturation, so 0.9 volts almost, but I use this divided by 4 because I need 25 milliampere only. So I got 0.225 millivolt. I use 0.225 volts or 0.225 volts here. So we have now the voltage across resistor, supply minus voltage base emitter saturation 11.75 Ohm's law here, 11.70 divided by the ampere at the resistor base, we got 56.1 kilo ohms or approximately 60 kilo ohms. We have pin out here, and I measured the actual value of the voltage drops in each component. This one is in theory almost the same. This one, when I change the value to 58 kilo ohms, not 60 ohms, it's almost the same in the meter or the tester. So we have now the value of RD here and RB. We now what? Oh my god, this one. Okay. Okay, we have the value of the RD here, RB. It's okay. Still, there's no problem with this floating kind of phenomena, because there is a series resistance here which is equivalent to the resistance of the current limiting resistor here of the diode. At the same time, there will be no reverse voltage happening here because there's a series resistance here. No need to put a pull down resistor here, because that pull down resistor is equivalent to the resistance of the breadboard and the wirings here. Since our there's no oscillating current here, the LED did not turn on. So it's okay that we don't have pull down resistor here, because there's already a series resistance here resistor. In this design, we don't need. There's already series resistance here, which is equivalent to the resistance of the breadboard and the wirings in the breadboard. Let's us build the actual circuit. This is the pin out of the C547C CBE. Let us check if there's no reverse voltage happening here. I think it's okay, even the switch is floating, or it will not conduct a current here. All the power will be dissipated in the resistor. Let us build the actual circuit if we need a pull down resistor or not. Okay, thank you.